Imagine two black holes, each heavier than the Sun, locked in a cosmic waltz just 300 million years after the Big Bang, so close their gravitational dance warps spacetime around them, yet so distant they've taken billions of years to reveal their existence. The James Webb Telescope has caught sight of this eerie pair, nestled in a primordial galaxy 13.5 billion light-years away, defying expectations. How? These ancient giants, born in the universe's infancy, shouldn't have survived long enough to form such a tight duo. Yet here they are, orbiting each other in a celestial ballet that challenges our understanding of black hole evolution. Their presence hints at a hidden universe of mergers and collisions, where the first stars collapsed into monsters, shaping the cosmos we see today. This isn't just a discovery, it's a mirror, reflecting the wild, untamed infancy of the universe itself. The James Webb Space Telescope has made a groundbreaking discovery that could reshape our understanding of the early universe. Scientists have identified the oldest and closest pair of black holes ever observed, dating back nearly 13 billion years. These two massive objects, located in the early cosmos, are not only ancient but also unusually close to each other, a finding that challenges existing theories about how black holes form and evolve. This discovery, announced in recent weeks, represents a major milestone in astrophysics, offering a rare glimpse into the universe's infancy and the role of black holes in shaping the cosmos. Black holes are among the most mysterious and powerful objects in the universe. Formed when massive stars collapse under their own gravity, they exert an almost unimaginable pull, trapping light and matter within their event horizons. For decades, astronomers have studied black holes to understand their behavior and their influence on the surrounding environment. Yet, many questions remain: how do they form? How do they grow? And what role do they play in the evolution of galaxies? These questions take on new urgency when considering the early universe, a period when the cosmos was still young and undergoing dramatic changes. The James Webb Telescope, launched in 2021, is uniquely suited to explore the early universe. Unlike its predecessors, Webb can peer through the cosmic fog that obscures distant objects by observing in the infrared spectrum. This capability allows it to detect light from the earliest stars and galaxies, which has been stretched and dimmed over billions of years. The telescope's advanced instruments have already revealed stunning images of star-forming regions in distant galaxies, but its latest findings push the boundaries of what we thought was possible. The discovery of these two black holes, which exist in the early universe, is a testament to Webb's power as a tool for uncovering the cosmos' hidden secrets. The black holes in question are part of a binary system, meaning they orbit each other in a tight, gravitational dance. What makes this discovery extraordinary is their age and proximity. These objects are among the earliest known black holes, formed just a few 100 million years after the Big Bang. Their existence suggests that black holes may have formed in the early universe under conditions very different from what we observe today. Moreover, their close proximity, far closer than most black hole pairs, raises intriguing questions about their formation. Did they form together from a single collapsing star, or did they merge from smaller black holes? The answer could provide critical insights into the life cycles of black holes and their role in galaxy formation. The significance of this discovery extends beyond the study of black holes themselves. In the early universe, galaxies were still in their formative stages, and the presence of such massive objects could have influenced the growth of these galaxies. Black holes, particularly supermassive ones, are thought to reside at the centers of galaxies, where they regulate star formation and shape the surrounding environment. If these two black holes are part of a larger system, their interactions could have played a pivotal role in the development of their host galaxy. Understanding their behavior in the early universe could help scientists piece together the timeline of cosmic evolution, from the first stars to the vast structures we see today. What makes this discovery even more remarkable is the fact that these black holes are so close to each other. Most black holes exist in isolation, but binary systems are rare and require specific conditions to form. The fact that these two black holes are in such a tight orbit suggests that they may have formed in a unique environment, one that was dense and filled with gas and matter. This could mean that the early universe was more chaotic and dynamic than previously thought, with conditions that allowed for the rapid formation of massive objects. The discovery also hints at the possibility of future mergers, as the gravitational pull between the two black holes could eventually lead to a collision, releasing a burst of gravitational waves detectable by observatories on Earth. The implications of this finding are far-reaching. For years, scientists have debated how black holes form in the early universe, with theories ranging from direct collapse of gas clouds to the mergers of smaller black holes. This discovery provides concrete evidence that at least some black holes formed in the earliest epochs, challenging existing models and prompting new questions. It also highlights the importance of the James Webb Telescope in uncovering these elusive objects. By capturing light from the distant past, Webb has opened a new window into the cosmos, allowing researchers to study the universe as it was billions of years ago. This discovery is not just a milestone in black hole research, it is a reminder of how much we still have to learn about the universe. The early cosmos was a time of extreme conditions, where the laws of physics may have operated differently, and where the seeds of today's galaxies were sown. By studying objects like these black holes, scientists can trace the history of the universe and uncover the processes that shaped it. As the James Webb Telescope continues its mission, it is likely to reveal more surprises, each one bringing us closer to understanding the origins of the cosmos and our place within it. The James Webb Space Telescope has rewritten the story of the early universe. For decades, scientists have peered into the cosmos, searching for clues about the first galaxies, stars, and the mysterious forces that shaped them. But until now, the most distant and ancient objects remain just out of reach until the Webb telescope, with its unprecedented power, revealed something extraordinary: the oldest and closest pair of black holes ever discovered. These two massive cosmic entities, locked in a binary dance, are not just relics of the past, they are a key to understanding how the universe evolved. But how did scientists find them? What tools and techniques allowed them to detect these ancient giants in the vast darkness of space? Let's step through the journey of discovery, from the moment the telescope was launched to the moment it captured these groundbreaking images. The James Webb Telescope is a marvel of engineering, a successor to the Hubble Space Telescope but far more powerful. Launched in 2021, it was designed to observe the universe in infrared light, a wavelength that allows it to see through the cosmic fog that obscured the earliest galaxies. Unlike Hubble, which primarily captures visible light, Webb's instruments can detect the faint, redshifted light from objects billions of light-years away. This capability is critical because the universe was once shrouded in thick clouds of gas and dust, making it nearly impossible to observe the earliest epochs. But with its massive mirror, 6 times larger than Hubble's, Webb can gather more light and resolve finer details, revealing structures that were previously invisible. This technological leap was not just about size, it was about vision, a vision that could pierce the veil of time to glimpse the universe's infancy. But even with such advanced tools, finding black holes is no simple task. Black holes themselves emit no light, so scientists must rely on indirect methods to detect them. One of the most promising approaches is to observe the light emitted by the material that spirals into a black hole, forming a glowing accretion disk. These disks, heated to extreme temperatures, emit radiation across the electromagnetic spectrum, including X-rays and visible light. However, the early universe was a chaotic place, filled with dense clouds of gas and dust, making it difficult to spot these faint signals. The Webb telescope's infrared capabilities are particularly valuable here, as they can detect the faint glow of distant galaxies and the warm glow of accretion disks, even when the light has been stretched by the universe's expansion. The discovery of the oldest black holes required more than just advanced technology, it demanded a deep understanding of the universe's history. Black holes are born in the violent deaths of massive stars, but in the early universe, the conditions were different. The first stars, known as population 3 stars, were much larger and more massive than today's stars, and their collapse could have produced black holes with masses hundreds of times that of the Sun. These primordial black holes, if they exist, would have been among the first structures to form after the Big Bang. However, detecting them has been a challenge, as they would have been surrounded by dense clouds of gas and dust, obscuring their light. The Webb telescope's ability to peer through this cosmic haze has made it possible to observe these ancient objects for the first time. The process of discovery began with the telescope's first observations, which were meticulously analyzed by a team of scientists. The data collected by Webb is vast. Each image contains billions of pixels, and each pixel represents a tiny piece of the universe's history. To make sense of this data, scientists use sophisticated algorithms and machine learning techniques to identify patterns that might indicate the presence of black holes. For example, they look for the telltale signs of gravitational lensing, where the gravity of a massive object bends the light from objects behind it, creating distorted or magnified images. This phenomenon can help scientists detect distant galaxies and black holes that would otherwise be too faint to see. But the discovery of the closest pair of black holes required a different approach. These two black holes, located in a distant galaxy, are not just ancient, they are unusually close to each other, a rarity in the universe. Most black holes are isolated, but some form binary systems, orbiting each other in a delicate balance. The Webb telescope's high-resolution imaging allowed scientists to detect the subtle gravitational effects of these two massive objects on their surroundings. By analyzing the way the light from the galaxy is distorted, they could infer the presence of the black holes and estimate their masses. This method, known as gravitational lensing, is a powerful tool for studying objects that are too distant or too faint to observe directly. The timeline of this discovery is as remarkable as the findings themselves. The James Webb Telescope began its mission in 2021, and over the following years, it has provided a steady stream of data that has transformed our understanding of the universe. The discovery of these black holes came from a combination of long-term observations and targeted studies. Scientists had to wait for the telescope to gather enough data to confirm their findings, a process that can take years. The first images of the early universe were stunning, revealing galaxies that had never been seen before, but the discovery of these black holes required a deeper dive into the data. By analyzing the light from distant galaxies, the team identified a unique signature that suggested the presence of two massive black holes in a binary system. The significance of this discovery cannot be overstated. These black holes are not just ancient, they are among the first to have formed in the universe, and their existence provides critical insights into the processes that shape the cosmos. Black holes are often referred to as the engines of galaxy evolution, as their gravitational pull can influence the formation and growth of galaxies. By studying these ancient black holes, scientists can better understand how galaxies formed and how their structures evolved over time. Additionally, the fact that these two black holes are so close to each other suggests that they may have merged in the past, releasing gravitational waves that could have rippled through the universe. This possibility opens new avenues for research, as scientists can now look for evidence of such mergers in the data collected by other observatories. But the journey to this discovery was not without challenges. The early universe is a complex and dynamic environment, and the data collected by the Webb telescope is a puzzle that requires careful interpretation. Scientists had to contend with the limitations of their instruments, the vast distances involved, and the sheer volume of data they were processing. Each observation required meticulous analysis, and the team had to rule out alternative explanations for the signals they detected. For example, they had to ensure that the light they observed was not from a different source or a chance alignment of objects. This level of scrutiny is essential, as even small errors can lead to incorrect conclusions about the universe's history. The discovery of these black holes also highlights the importance of collaboration in modern astronomy. The James Webb Telescope is a multinational project, involving scientists from around the world, and the analysis of its data has required a global effort. Teams of researchers have worked together to develop new algorithms, refine their methods, and share their findings. This collaborative spirit has been crucial in overcoming the challenges of studying the early universe and has led to breakthroughs that would have been impossible to achieve alone. The discovery of these black holes is a testament to the power of science when it is driven by curiosity, innovation, and teamwork. As we reflect on this discovery, it becomes clear that the James Webb Telescope is more than just a tool, it is a window into the past, a bridge between the present and the ancient cosmos. The ability to observe the earliest galaxies, the first stars, and now the oldest black holes represents a new era in astronomy. Each discovery brings us closer to understanding the fundamental forces that shape the universe and the mysteries that still lie ahead. The journey of the James Webb Telescope is just beginning, and with every new observation, it continues to rewrite the story of the cosmos. The oldest black holes may have been found, but the universe still holds countless secrets waiting to be uncovered. The discovery of the oldest and closest pair of black holes in the early universe, made possible by the James Webb Space Telescope, represents a pivotal moment in our understanding of cosmic evolution. These black holes, observed in the universe's infancy just 500 million years after the Big Bang, challenge existing theories about how such massive objects form and how they influence the development of galaxies. To grasp the significance of this finding, we must first consider the fundamental role black holes play in the universe and how their existence is intertwined with the life cycles of galaxies. Black holes are not mere cosmic voids, they are powerful engines that shape the structure of the cosmos. At the centers of most galaxies, supermassive black holes, millions or even billions of times the mass of the Sun, exert gravitational influence over entire systems of stars. Their presence is thought to regulate star formation, control the flow of gas, and even determine the fate of their host galaxies. Yet, the formation of these titanic entities remains one of the most enduring mysteries in astrophysics. How did such massive black holes arise so quickly after the Big Bang? And what does their existence in the early universe tell us about the conditions that shaped the cosmos? The James Webb Telescope, with its unprecedented sensitivity to infrared light, has allowed astronomers to peer deeper into the universe than ever before. By capturing light from the earliest stars and galaxies, it has provided a window into the universe's first few 100 million years, a period so distant and obscured by cosmic dust that previous telescopes could only glimpse its edges. The detection of these two black holes, located just 1.5 billion light-years away, marks a breakthrough in our ability to study the early universe. Their proximity to one another, despite the vastness of space, suggests a unique formation scenario. Typically, black holes are found in isolation, but this pair appears to be gravitationally bound, orbiting each other in a system that may have formed alongside the galaxy they inhabit. This discovery raises profound questions about the mechanisms that govern the birth and growth of black holes. One prevailing theory suggests that the first black holes formed from the collapse of massive, short-lived stars, so-called population 3 stars. These stars, composed almost entirely of hydrogen and helium, were thought to be the progenitors of the first black holes. However, the rapid formation of supermassive black holes in the early universe has long puzzled scientists. How could such massive objects grow so quickly? The existence of these two black holes, which may have formed together, offers a potential clue. If they originated as a binary system, their mutual gravitational pull could have provided the necessary conditions for rapid growth through accretion of surrounding gas. This scenario aligns with recent models that propose black holes can form in pairs, either through direct collapse of gas clouds or the merging of smaller black holes. The implications of this discovery extend beyond the study of black holes themselves. Galaxies and black holes are deeply interconnected, with their growth often occurring in tandem. The presence of a supermassive black hole at the center of a galaxy can influence the rate at which stars form, preventing excessive star formation by heating and expelling gas. Conversely, the availability of gas can fuel the growth of the black hole. This symbiotic relationship, known as galaxy black hole coevolution, is a cornerstone of modern astrophysics. However, the discovery of these two black holes challenges our understanding of this process. If they formed in the early universe, their existence suggests that the conditions for rapid galaxy and black hole growth were already in place just 500 million years after the Big Bang. This implies that the processes driving galaxy formation and black hole growth may have been more efficient or accelerated in the early cosmos than previously thought. Moreover, the proximity of the pair raises intriguing questions about their future. Binary black holes are expected to eventually merge, releasing gravitational waves that ripple through spacetime. These mergers are detectable by observatories like LIGO and Virgo, which have already detected dozens of such events. However, the detection of these particular black holes in the early universe could provide insights into the population of binary black holes in the cosmos and their role in the overall energy budget of the universe. The James Webb Telescope's ability to detect these objects also highlights the technological advancements that have made such discoveries possible. Unlike its predecessors, which struggled to penetrate the thick clouds of dust that obscured the early universe, JWST's infrared capabilities allow it to see through these barriers. This has enabled astronomers to study the structure and dynamics of galaxies in their infancy, revealing details about their composition, star formation rates, and the distribution of dark matter. The discovery of these black holes is a testament to the power of these instruments and the collaborative efforts of the global scientific community. Yet, this finding is not just a milestone in observational astronomy, it is a catalyst for new theories and models.
The existence of such ancient black holes may force scientists to reconsider the timeline of galaxy formation and the role of dark matter in shaping cosmic structures.
Dark matter, which makes up approximately 27% of the universe's mass, is thought to provide the gravitational scaffolding upon which galaxies form. However, its direct interaction with ordinary matter remains elusive. The presence of these black holes in the early universe could offer clues about how dark matter influenced the formation of the first galaxies and, by extension, the first black holes. Additionally, the discovery may shed light on the reionization epoch, a period in the universe's history when the first stars and galaxies began to ionize the surrounding hydrogen gas. This process, which transformed the universe from a dark, neutral state to one filled with ionized plasma, is believed to have been driven by the ultraviolet light emitted by the first stars. The presence of these black holes, which may have been powered by the accretion of gas from the early universe, could have played a role in this reionization process. Their intense radiation might have contributed to the ionization of the intergalactic medium, accelerating the transition to the universe we observe today. As we continue to analyze data from the James Webb Telescope, the implications of this discovery will likely ripple through multiple areas of astrophysics. The study of black holes, galaxy formation, dark matter, and the early universe's evolution are all interconnected, and this finding provides a rare opportunity to observe these processes in action. The detection of these two black holes not only deepens our understanding of the cosmos but also underscores the importance of continued exploration. Each new discovery, no matter how small, brings us closer to unraveling the mysteries of the universe. In the vast expanse of space, where time and distance stretch beyond human comprehension, such findings remind us that the universe is still full of surprises. The James Webb Telescope has opened a new chapter in our cosmic story, and the study of these ancient black holes is just the beginning of a much larger narrative, one that continues to unfold with every new observation and every question we dare to ask. For decades, the universe has been a vast, mysterious expanse, its secrets revealed one discovery at a time. The story of black holes is one of those revelations, beginning with a single equation, then evolving into a cornerstone of modern astrophysics. In 1915, Albert Einstein's theory of general relativity predicted the existence of these cosmic entities, regions of space where gravity is so intense that not even light can escape. At first, the idea seemed almost fantastical, a mathematical curiosity rather than a physical reality. But by the 1960s, astronomers began to find indirect evidence of black holes. They observed quasars, brilliant, distant objects powered by supermassive black holes at the centers of galaxies. These findings hinted that black holes were not just theoretical constructs but real, ancient phenomena shaping the cosmos. Yet, the question remained, how did these massive objects form, and what role did they play in the evolution of galaxies? Over the decades, telescopes and instruments have steadily advanced, peering deeper into the universe's history. The Hubble Space Telescope, launched in 1990, became a key player in this quest. Its ability to capture light from distant galaxies allowed scientists to study the growth of supermassive black holes and their relationship with their host galaxies. But Hubble had its limits. Its instruments could only detect light in certain wavelengths, and the universe's earliest epochs, when galaxies and black holes first formed, remain shrouded in mystery. Enter the James Webb Space Telescope, launched in 2021. With its advanced infrared capabilities, Webb can peer through cosmic dust and observe objects from the early universe, where light has traveled for billions of years to reach us. This new era of observation has already rewritten our understanding of the cosmos. Recently, Webb's instruments have uncovered a discovery that challenges previous assumptions: the oldest and closest pair of black holes ever observed in the early universe. This finding is more than just a record, it's a critical piece in the puzzle of how black holes and galaxies evolved together. To appreciate the significance of this discovery, we must look back at the journey of black hole research. The 1960s and 1970s were a time of breakthroughs. Astronomers like Subramanian Chandrasekhar and John Wheeler refined the theory of black holes, while observations of X-ray binaries systems where a black hole pulls material from a companion star provided direct evidence of their existence. By the 1980s, the concept of supermassive black holes at the centers of galaxies had gained traction. The discovery of active galactic nuclei, where immense energy is emitted from a black hole's accretion disk, further solidified their role in galaxy evolution. Yet, the question of how these massive objects formed remained unanswered. Did they grow from smaller black holes over time, or did they form directly from the collapse of massive stars? The answer to this question has profound implications for our understanding of the universe's history. In the 1990s and 2000s, the Hubble Space Telescope provided crucial insights. By studying the light from distant galaxies, astronomers could measure how their central black holes grew over time. These observations suggested a correlation between the mass of a black hole and the mass of its host galaxy, implying a deep connection between the two. However, Hubble's ability to peer into the early universe was limited by its optical instruments. The light from the earliest galaxies, formed just a few 100 million years after the Big Bang, was stretched into infrared wavelengths by the expansion of the universe. To study these ancient objects, astronomers needed a telescope that could detect infrared light with unprecedented precision. This led to the development of the James Webb Space Telescope, a mission decades in the making. Launched in 2021, Webb's primary mirror, nearly 3 times larger than Hubble's, and its advanced infrared sensors allowed it to capture light from the universe's infancy. Its ability to observe in the near and mid-infrared ranges meant it could see through the dust that obscures young stars and galaxies, revealing structures that were previously hidden. With Webb's gaze, astronomers have already made groundbreaking discoveries. One of the most significant was the detection of the earliest galaxies, formed just 300 million years after the Big Bang. These galaxies, though small and faint, provided clues about how the first stars and black holes formed. But the recent discovery of the oldest and closest pair of black holes in the early universe represents a new milestone. This finding challenges previous assumptions about the formation and distribution of black holes in the early cosmos. Until now, the closest known black hole pairs were found in more recent galaxies, but Webb's observations have revealed a pair in a galaxy that formed just 1.5 billion years after the Big Bang. This discovery is significant because it suggests that black holes may have formed earlier than previously thought, and that their interactions, such as mergers, could have played a role in shaping the early universe. But how did astronomers arrive at this conclusion? The process began with Webb's ability to detect faint, distant light. By analyzing the light from these ancient galaxies, scientists could infer the presence of black holes. The key lies in the way black holes interact with their surroundings. When a black hole accretes matter, it emits radiation that can be detected across the electromagnetic spectrum. Additionally, when two black holes orbit each other, they emit gravitational waves, ripples in spacetime that can be detected by instruments like LIGO and Virgo. However, gravitational waves from the earliest black hole mergers would be too faint for current detectors, making direct observation difficult. Instead, astronomers rely on indirect methods, such as studying the light from galaxies and their central black holes. The recent discovery of the closest pair of black holes in the early universe was made possible by Webb's ability to observe in the infrared, where the light from these ancient objects is most visible. By analyzing the light from these galaxies, scientists could detect the signatures of black holes, such as their influence on the surrounding gas and stars. The fact that these black holes are so close to each other suggests that they may have formed in a dense environment, perhaps within a collapsing gas cloud or a cluster of stars. This scenario aligns with theories that suggest black holes can form in dense regions, where the conditions are right for their rapid growth. However, the discovery also raises new questions. How did such massive black holes form so quickly? Previous models suggested that black holes grow over time by accreting gas and merging with other black holes, but the existence of these ancient pairs implies that their formation process may have been more complex. Some scientists propose that these black holes could have formed directly from the collapse of massive stars, bypassing the slower growth processes. Others suggest that they may have formed in a different way altogether, perhaps through the merging of smaller black holes in the early universe. These theories are still being explored, and the James Webb Telescope's observations are providing crucial data. The discovery of these black holes is not just a milestone in black hole research, it's a testament to the power of modern astronomy. It shows how far our understanding has come, from the theoretical predictions of Einstein to the direct observations made possible by advanced telescopes. Yet, the journey is far from over. Each new discovery opens up new questions, and the search for answers continues. As we look to the future, the James Webb Telescope and other next-generation instruments will play a vital role in unraveling the mysteries of the universe.
the study of black holes and their role in shaping galaxies remains
one of the most exciting frontiers in science. And with every new observation, we take another step closer to understanding the cosmos and our place within it. The discovery of the oldest and closest pair of black holes in the early universe has sparked a wave of excitement and questions among scientists. These two black holes, observed by the James Webb Space Telescope, are not just remarkable for their age but also for their proximity to each other, challenging existing theories about how such systems form. While the findings offer a glimpse into the cosmos' early history, they also raise profound uncertainties about the processes that shaped the universe. For instance, how could two black holes form so early in the universe's timeline? And why are they so close to each other, defying expectations about the vast distances between celestial objects? These questions are not just academic, they are critical to understanding the fundamental forces that govern the universe. The James Webb Telescope's ability to peer back in time has allowed scientists to observe these black holes as they existed just a few 100 million years after the Big Bang, but the data they've collected also highlight gaps in our current knowledge.
For example, the mechanisms by which black holes form in such an early epoch remain unclear.
Traditional models suggest that black holes grow over time through accretion of gas and mergers with other black holes, but these processes typically take billions of years. The existence of such a pair so soon after the Big Bang suggests that there may be alternative pathways for black hole formation or that our understanding of cosmic timelines is incomplete. Additionally, the proximity of these two black holes raises intriguing questions about their dynamics. In the vast emptiness of space, the average distance between celestial objects is immense, but these black holes are unusually close. This could imply that they formed in a dense environment, perhaps within a collapsing gas cloud or a star-forming region, but the details remain speculative. Scientists are now grappling with the implications of these findings, considering whether they point to new physics or simply highlight the limitations of current models. The discovery also invites comparisons to other observed phenomena, such as the formation of binary star systems, which are more common in the universe. However, the scale and energy involved in black hole systems are vastly different, making direct comparisons challenging. Another layer of mystery surrounds the role of dark matter in the formation of these black holes. While dark matter is thought to play a crucial role in the large-scale structure of the universe, its exact interactions with black holes are still poorly understood. The presence of such a close pair of black holes might suggest that dark matter influenced their formation in ways we have yet to comprehend. Moreover, the observation of these black holes provides a unique opportunity to study their gravitational effects. Black holes are known for their intense gravitational pull, but the specifics of how they interact with their surroundings, especially in the early universe, are still under investigation. For example, the gravitational waves emitted by merging black holes could offer insights into their properties, but detecting such signals requires advanced technologies and precise measurements. The James Webb Telescope's ability to capture detailed images of these distant objects is a testament to its capabilities, yet it also underscores the challenges of observing such faint and distant phenomena. The data collected so far may not yet provide a complete picture, leaving room for further exploration. Scientists are also questioning the implications of these findings for the broader understanding of galaxy evolution. Black holes are often found at the centers of galaxies, and their growth is thought to be linked to the evolution of their host galaxies. However, the presence of a close pair of black holes in the early universe could suggest that galaxies formed in a different way than previously believed. This could mean that the relationship between black holes and their host galaxies is more complex than currently modeled. Additionally, the discovery raises questions about the role of supermassive black holes in the early universe. While supermassive black holes are known to exist in the centers of galaxies today, their formation in the early universe remains a topic of debate. The observed pair of black holes might represent a different type of system, or they could be precursors to the supermassive black holes we see today. These possibilities highlight the need for further research and the development of new observational techniques. The scientific community is also considering the possibility that these findings could challenge existing theories about the universe's expansion. The early universe was a period of rapid growth, and understanding how structures like black holes formed during this time is essential for refining cosmological models. However, the data from the James Webb Telescope may reveal discrepancies that could lead to new insights or even revisions of current theories.
Another area of debate centers around the methods used to detect and analyze these black holes.
While the James Webb Telescope has provided unprecedented clarity, the interpretation of its data is not without challenges. For example, distinguishing between the light emitted by the black holes themselves and the light from surrounding material requires sophisticated analysis.
Any errors in this interpretation could lead to mischaracterizations of the black hole's properties.
Furthermore, the sheer scale of the universe means that even with advanced technology, there are limits to what we can observe. The James Webb Telescope has expanded our reach, but it cannot see everything, and some phenomena may remain beyond our current capabilities. This underscores the importance of continued exploration and the development of new technologies to push the boundaries of our understanding.
The discovery of these black holes also has implications for the study of other cosmic phenomena.
For instance, the presence of such a close pair could influence the behavior of nearby stars and gas, potentially affecting the formation of other celestial objects. However, the exact nature of these interactions is still unclear, and further observations are needed to determine their significance. Additionally, the study of these black holes could provide clues about the distribution of matter in the early universe. By analyzing their positions and movements, scientists might gain insights into the large-scale structure of the cosmos and the role of dark energy in its evolution. Yet, these insights are still in their infancy, and much work remains to be done. The scientific community is also aware that this discovery is just one piece of a much larger puzzle. While the James Webb Telescope has provided valuable data, the full picture of the universe's history is still being assembled.
Each new observation adds to our understanding, but it also raises new questions that require innovative approaches and collaborative efforts.
In this context, the discovery of the oldest and closest pair of black holes serves as both a milestone and a catalyst for further exploration. It reminds us that the universe is full of mysteries waiting to be uncovered, and that our quest for knowledge is an ongoing journey. As scientists continue to analyze the data and refine their models, they are likely to uncover new insights that could reshape our understanding of the cosmos. The study of these black holes is not just about their existence but about the broader implications for the fundamental laws of physics and the history of the universe. Ultimately, this discovery highlights the importance of curiosity and the pursuit of knowledge in the face of the unknown. It is a reminder that even the most advanced technologies have limits, and that the mysteries of the universe will continue to challenge and inspire us. The journey to unravel these mysteries is just beginning, and the next steps will depend on the collective efforts of scientists, engineers, and explorers who are driven by the desire to understand the cosmos. James Webb Telescope just spotted the oldest, closest pair of black holes in the early universe. This part of our deep dive into James Webb Telescope just spotted the oldest, closest pair of black holes in the early universe focuses on, explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. James Webb Telescope just spotted the oldest, closest pair of black holes in the early universe. This part of our deep dive into James Webb Telescope just spotted the oldest, closest pair of black holes in the early universe focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.